Hello viewers, welcome to this second episode of our lecture series on elementary quantum mechanics. You would recall that in the first episode we talked about the basic premise of classical mechanics. We saw how does it explain the macroscopic phenomenon. Thereafter we took up two experiments, that is a black body radiation and photoelectric effect, to establish that the classical mechanics is inadequate to explain the results of this experimentation. And continuing from there, today we will take up three more experiments to substantiate that inadequacy of classical mechanics to deal with systems which are microscopic in nature, that is constituted of atoms, molecules and things like that. And in this second part of our demonstrating inadequacy of classical mechanics, I will try to take up three more experiments, that is the anomalous heat capacity of solids, atomic line spectrum and Compton scattering, and then we will see that what are the experiments, what is the kind of results obtained, what are the classical predictions, and then we will see to what extent there is a mismatch between theory and experiment, and in the process we will try to demonstrate the inadequacy of classical mechanics, and then towards the end we will try to sum up where do we stand. Let us make a beginning by talking about anomalous heat capacity of solids. Now, what is the heat capacity? This is a very simplified version of a law which is given by Dulong and Petit. What Dulong and Petit observed was that the specific heat of these solids multiplied by their atomic weight happens to be a constant. It is a very simplified observation, and that holds true for wide variety of solids. It held true because at that point of time whatever solids were available, he tried to measure them and then try to document them together in an empirical way, and they happen to be reasonably constant. That is, it happens to be about 6.4 calories per degree per gram atom, and the modern value nowadays quoted is about 25 joules per degree Kelvin per mole. The specific heat is the amount of heat required to raise the temperature of a unit mass of a substance through 1 degree centigrade. That specific heat into the atomic mass gives you a constant, and what we found was that most of solids what were measured at that point of time, that is around early 19th century, they happen to give this a constant value. That is what is Dulong's Petit law, and probably this law came into being for the reasons that the measurements at that point of time were done at normal temperatures, room temperature, or maybe slightly above and slightly below that. And the experimental observations were that this law holds for reasonably moderate temperature or high temperature, room temperature around that, and also there is a good agreement with large number of solids, whereas for some solids the values were slightly lower than this predicted by this law. However, within the range this law held fairly well. However, when experimental measurements were made at temperatures below room temperature, far below room temperature, that means when cryogenics came into being, at that stage we found that there is a marked contrast, marked deviation from prediction. That means the values were much less than what is predicted by this law, and to the extent that at absolute zero they approached to a value of 0. This behavior of a steep decrease in the molar heat capacity of solids at low temperature is referred to as the anomalous heat capacity of solid. Now, to this effect, if we try to see classically what do we expect, and the classical prediction according to Boltzmann is that from thermodynamics we can derive an expression which says that Cv is equal to 3R, that is a molar heat capacity at constant volume is 3R, R is a gas constant, that gives a value of about 6 calorie per mole. That is what is predicted by Dulong's and Petit law. That means a fairly good agreement is there. The classical prediction does not talk anything about temperature dependence. That means classically speaking, the molar heat capacity should not depend on temperature. That is where the whole catch is. That is, classically this value of 6 calorie per mole or 24.94 joules per Kelvin per mole is perfectly fine, but at low temperature there is a deviation. That is where the theory and experiment do not match. So, what you find is again there is an instance where the classical predictions and experimental observations do not match, and we need to have some theory which can take care of this. And such an explanation was given by Einstein in 1907, which was further improved by Debye in 1912, about which we will talk in the next episode. Now, let me take second experiment for today, that is the fourth experiment in our sequence of steps, a sequence of experiments we are taking up, that is atomic line spectrum. This is very, very crucial because that has a bearing on our understanding of atomic structure as we know of today, especially the Bohr's model. We know that hot objects give continuous spectra. You would recall that in black body radiation we talked about, there was a whole range of wavelengths coming out there. To understand continuous spectrum, I will give you an example of a rainbow. If you look at the rainbow, what you find is there is a whole spectrum, VIBGYOR, from violet, indigo, blue, green and so on to red. There is a whole spectrum. That means in this rainbow, we have all different wavelengths in the visible range which are shown over there. That means all radiations are present in that. Typically, another example I am showing you here is, suppose I take a simple light bulb. If I take the hot filament in the bulb, is giving out white radiation. If I pass that radiation through a slit and make it fall on a prism, what I find is that the prism disperses different radiations according to their wavelengths, and what I find is a whole range of a spectrum coming over there. This is a typical example of a continuous spectrum. A continuous spectrum means a spectrum which has whole range of frequencies or the wavelengths present in that. So, the radiations which come from a hot filament of a bulb or incandescent bulb consist of a continuous range of wavelengths. That is a common phenomenon we have with us. Now, as against that, since we, I am sure that most of us belong to chemistry discipline and would have done at some stage in our career, we have done some kind of salt analysis, and in that process we do what is called as a flame test. What we do is we typically take the sample to be analyzed and put it on the flame, and what you find is that sample, say suppose it contains sodium atom or something like that, that imparts a characteristic color to the flame. That is called as a flame test. That is used for identification of different cations in the system. I have given you some examples over there. You know that lithium ions will give you, it imparts red color to the flame, sodium gives you a yellow color. That is what I am showing over here in this demonstration here. In this picture here, potassium gives you violet, rubidium gives purples and so on and so forth. So, what you find is that different metals, so to say, give characteristic color to the flame, and they can be used for their identification as well. But what is important for me here is, let me take this example now. In this picture I am showing you 3 different flames coming from such a flame test. These belong to that of lithium, sodium and potassium. Now, what is important is that if I take any of these, say I take lithium, the flame from lithium, and make this light pass through a prism, which I showed you in the previous case there. When I pass it through prism and then I see what is the outcome here, what I find is that there will be a set of lines coming over here. Similarly, for sodium, this is a set of lines coming there at 589 nanometer, and for potassium you get these set of lines over there. So, what you find is the characteristic spectra of this metal ions or hot metal ions, they happen to be discrete lines. It is in sharp contrast to what we had in case of continuous spectrum. In continuous spectrum, we have got all wavelengths. It is from about 370 nanometers to about 750 nanometers. That is the visible range we have. Okay. So, in case of a white light passed through prism, I get whole range of wavelengths from 370 nanometers approximately to about 750 nanometers. As against that, when I pass this flame, there is a color of this flame, where I observe there the light coming out of this flame, when I pass through prism, I get only a few lines over there in the spectrum and not the whole thing. So, this is an example of a line spectrum as contrast to a continuous spectrum. So, this kind of observation of a line spectra is again something which is difficult to explain from classical mechanics. Let us see what do we expect from classical mechanics. And before I come to even that, let me take one more example here. If I take say a hydrogen lamp, if I take hydrogen lamp, because this particular one has a very significant bearing on the our atomic structure understanding. Well, I will talk about that little later as well. What I find is if I take this hydrogen lamp and the light which is coming from hydrogen lamp is passed through prism again, gets dispersed. What you find is this gives you very characteristic set of lines over there. These set of lines again, they are basically the typical hydrogen atom spectrum, and for any model of an atom to be established or to be acceptable, it must be in a position to explain the origin of these lines. That is why I just said that this is a very, very crucial experiment for us. Now, but what is important here is in our argument which I am trying to put forth here, that these are again a line spectra. This line spectra what we obtained for hydrogen atom was actually kind of put together in terms of an expression of this kind, which is 1 by lambda is equal to RH 1 by and so on and so forth. What it means is that empirically all these wavelengths at which these radiations are coming out can be expressed in terms of the following expression. That means all these the positions at which these lines are coming, they are related to each other by this formula, and since this was done by Balmer, so this is called as Balmer's series, whereas this RH happens to be a constant called as Rydberg constant, whose value was found to be this much empirically. Now, and what we see is that these lines here what we obtained here, they can be rationalized in terms of different values of n. So, we put a value of n to be 3, because we see is that n are integers greater than 2. Okay. So, when n is 3, that gives you one line, n is 4, second line, 5, third line, and so on and so forth. I keep on taking the different values of n, I get different values of the radiation which are coming out there. So, these radiations are dependent on the value of n. Similarly, there were many more series of such lines were observed. They are named as on the basis of who discovered them. One is called as Lyman series. This was observed in X-rays in the UV region, because Balmer series was in the visible region. Lyman series was in the X-ray and UV region. Paschen series is in the short wavelength IR. Brackett series is in the long wavelength IR region, and all of them could be formulated empirically in terms of expression similar to what we had in case of Balmer series, but the only difference was the value of n had to be different, because the expression here, this should be 1 by 1 here, say 1 by 1 square, or you can put it as 1. In this case it is, in case of Balmer series it was 1 by 2 square, and Lyman series it is 1 by 1 square, Paschen series 1 by 3 square, 1 by 4 square, and so on and so forth, and n will be 1 larger than the previous number here. So, in this case if n is equal to 1, the n here will be 2, 3, 4, and so on and so forth. In this case, so this number is 3, so n will be having a value of 4, 5, 6, and so on and so forth. So, what is important is that all this set of lines which we observe in case of hydrogen atom spectrum, whether they are in the visible range, IR range, UV, or otherwise, they all could be rationalized in terms of a general formula. Now, the important thing is that why should we get this? Because should we get this according to the classical mechanics? Let us try to have a look at that. Classically, if you look at the atom at that point of time, what we had was typically an understanding of atom in terms of Rutherford's model. What it says was there is a nucleus in the center and electron is moving around the nucleus. Now, when electron is moving around the nucleus, it can take up any energy, classically speaking. When it can take up any energy, so as electron is moving around the nucleus, it will be radiating different kinds of energies. That means it will give out radiations of different energies or different wavelengths, and in principle the emission spectrum which will come from a hot hydrogen atom should consist of a whole range of frequencies. A continuous spectrum is expected. What we got in contrast to this was that we got discrete lines, just well defined set of lines over there. So, we find again that as against a continuous spectrum expectation, what we experimentally got was a set of discrete lines. That is, once again we find that there is a sharp contrast to what we experimentally observe and what is theoretically expected from classical mechanics, or in other words, again classical mechanics is inadequate to explain the observations of this line spectra, typically of hydrogen atom, the simplest case. And an effective explanation to this was given by Niels Bohr in 1913 on the basis of concept of quantization, about which we will learn in the next episode. Okay, so where have we come so far? We have come to, in the first episode, we talked about two important phenomena and we found that classical mechanics was inadequate. Now we have taken two more instances, one of the heat capacity of solids at low temperatures and second of line spectrum. In both the cases, we have seen the classical predictions and the classical predictions and experimental observations do not match. Let me take one more case, that is of Compton scattering. I just mentioned earlier also in my last episode that Compton scattering actually was not a challenge per se to classical mechanics, because in fact it was kind of experiment designed to establish or verify the photon concept given by Einstein. But since the observations of Compton scattering cannot be rationalized in terms of classical mechanics, so I thought of clubbing it over here so that it falls in line. Let's see what is experiment and what is observation and then what is classical prediction in this case. What we do is we throw X-rays or we make X-rays fall on a sample of a solid. Say typically it was taken to be graphite. What was observed was that when X-rays were made to fall on graphite, when they got scattered from there and came back, in the scattered radiation it was observed that the wavelength of scattered radiation was longer than the one which was incident on the graphite. That is our first significant observation. And second was this wavelength of the scattered radiation depended on at what angle is the scattering taking place. There were two significant observations what we had in this case. And third, even we can put even the third one over there, that is the change in wavelength was dependent on the angle at which the scattering is taking place. Okay. So, there are three crucial observations in this case. And what is classically expected was that suppose this is my radiation which is coming on, this is an electron in my target say graphite, there is just one, I am depicting one electron in that case. So, what is classically expected is when this radiation comes, we know that radiation is essentially a wave, that is classical visualization there. When this wave, there is an electron there, this wave is coming there. So, what will happen is this wave is basically an oscillatory charge, oscillatory electrical field is coming. This oscillatory electrical field will put this electron into oscillation. That means this electron now which gets into oscillation becomes a source of, it becomes an emitter now. When it emits radiation, suppose this is coming with a certain frequency, say 500 cycles per second. So, this electron will get into oscillation at the same frequency of 500 cycles per second. In turn, this will become a source of radiation of 500 cycles per second, that means it will radiate in all possible directions with the same wavelength. That is, classically speaking, what I expect is that when a radiation falls on a target, it puts the electron in that into oscillation at the same frequency, which in turn becomes an emitter of same frequency. That is, theoretically speaking or classically speaking, what I expect is that the wavelength of incident radiation and the scattered one should be same and not different as was experimentally observed. So, to that extent what you find is that the classical predictions and experiment again do not match. So, we can very comfortably say that again our classical mechanics is inadequate to explain the results of our Compton scattering, and this the scattering phenomenon was later on explained by Einstein in terms of the concept of photon and all. We will talk about that in the next episode. Okay. So far where have we reached and what do we conclude from all this? What we have seen in these two episodes, the first one and the today's one, is that classical mechanics is inadequate to explain the results of following experiments: black body radiation, photoelectric effect, heat capacity of solids at low temperatures, line spectrum, that is from hot gases and all, and Compton scattering. And it amounts to saying that we need a new theory that can explain the experimental observations of such phenomenon, and that theory is quantum mechanics, about which we will learn in the next episode. Okay. So, we have to come to a conclusion. Now, quickly let us summarize what we have done so far. Broadly speaking, what we have done today is that we reviewed the contents of the previous lecture. Thereafter, we stated Dulong's and Petit's law on heat capacity of solids, and we talked about the anomalous deviation from this law at low temperature. That is the second thing we did. Thereafter, we demonstrated the inadequacy of classical mechanics in explaining this anomaly in the variation of heat capacity. Thereafter, we discussed the nature of line spectra and again the inadequacy of classical mechanics in explaining their origin. Thereafter, we took up the phenomenon of Compton scattering and once again kind of demonstrated the inability of classical mechanics to explain the same. And in this whole process, we have been able to establish the need of a theory that can explain the results of the experiments we have just listed about here. And that theory I am referring to here is what is called as quantum theory, or the concept of quantization, about which we will talk about in the next episode. We will talk about what is the meaning of quantization, who proposed it, in what context, and in what way this concept of quantization explained all these inadequacies of classical mechanics. That we will be taking up in the next episode.